So we've all been there. You're out with your elephant one day. You're on the ground floor and you got to get up one story. How are you going to do it? Well, you're probably going to have to take the stairs. But the question will arise, are the stairs strong enough? And today we are going to be answering that question with science. As usual, we're going to start with some theory. Then we're going to look at some code. Then we're going to finally wrap it all up with the easy way. So we're going to start our discussion of the theory of beam bending with the idea of unbraced length. What you see in this drawing here is some beam braces at some spacing. I don't know what it is. I'm just going to assume it's 6 feet on center. And that is showing you the unbraced length. You see these kinds of braces in all kinds of beam construction. We're going to see why that is a little bit later on. So this chart here is, to me, the most important chart in beam theory. On the y-axis, you have the moment capacity of your beam, and that is the bending strength of the beam. Along the x-axis is your unbraced length, which we saw on the previous slide is the distance between braces. Again, this is not the beam length. The next thing that you're going to notice when you're looking at this chart is that you've got the idea of a compact beam and a non-compact beam. And once again, we're going to get later in this to what is the difference between a compact beam and a non-compact beam are. Then you're going to see that there's this dashed line, and that's when your C sub B is greater than 1. And the solid line in the event is that your C sub B is equal to 1. Again, that's why this chart is maybe the most important chart that we have in beam theory, because there's just a lot that's happening in this chart, and it kind of sums up a lot. So then in terms of the strength of the beam, you see down here, this between 0 and L sub P, that's where your beam is going to be experiencing plastic deformation as its primary mode of failure. Between L sub P and L sub R, you have a partially elastic lateral torsional buckling, and we'll be looking at that a little bit later. Beyond L sub R, you've got a fully elastic lateral torsional buckling, and once again, we'll look at all that. But before we do, we're just going to kind of get back to column theory. It's the idea of a slender, a non-compact, or a compact section. Over here on the left, we have a compact section, and so when we are compressing that, it's going to squish. You know, it's not gonna bow out. It's not gonna experience that Euler buckling. The non-compact section is halfway between a compact section and a slender section. For the non-compact selection, for the non-compact section, you get some amount of elastic buckling, but also there's some plastic permanent deformation that occurs. And then for the slender element, when your B over T is 25 or greater, then you've got a fully elastic pop. It's if you had a piece of spaghetti, don't hit the microphone, David. If you had a piece of spaghetti and you, which you didn't cook, and you smashed it, you would have a fully elastic Euler buckling in that piece of spaghetti. Whereas if you cut that piece of spaghetti until it was just maybe half an inch long and tried to smash it, then it would be a plastic failure. I mean, not exactly, but you know, because spaghetti is not ductile when it's raw. So again, you know, this is the compact is plastic, non-compact is partially elastic, slender, fully elastic. So what does that look like on a beam flange? And this gets us into some of the other concepts shown on this chart. When this beam is going through bending, we're assuming that the force is down. And what that is going to do is going to put the top flange into compression, and like so, and the bottom flange into tension. And so the top flange it feels like a column under compression. And so much like that piece of spaghetti that wants to pop out, the top flange in this region that we see deformation is also inclined towards buckling. Now, if it's been designed in such a way that the top flange is only experiencing plastic deformation. Now you've got a compact section. Now the thing about it is, for most steel stair construction, you're doing, that was not supposed to happen. Don't skip ahead, David. You're dealing with either, C12 by 20.7 or an MC12 by 10.6. Was it 0.6? Maybe it was 0.6. And those sections are both compact. So what does that mean for our stair stringers, you may be inclined to ask? Well, as it turns out, typically our stair stringers are braced at 11 inches on center. Each of these risers has a weld up at the top and a weld up at the bottom. And those welds prevent the stringer from twisting and engaging in the lateral torsional buckling right there. And so that means that typically when we are designing stairs, even though I've gone over this whole beam bending theory, because it's important if you're designing these things in practice, because you're often going to come across times where this is not the case. But for your typical stair stringer, you're using a compact section and you are braced at 11 inches on center. So you are only in this portion of the graph, which makes the calculator we're going to look at quite a lot easier, because for moment capacity of the beam, the only thing you have to worry about is what is the yield strength and the moment of inertia for that beam. You don't have to worry about anything else so long as you've got your bracing 11 inches on center. So we're going to get to the code now, which we're going to start, as always, with your local code, which for us, it's 2022 California Building Code. We're going to look in chapter 35, and we're going to see that the AISC 36016 is listed as the referenced steel chapter. We're going to go into the specification at the back, and we're going to find table F1, and it's going to show you which of the sections you want to use, chapter sections you want to use for which steel section. So for us, oftentimes with stairs, we're just working with C channels. And so we're going to use chapter F sometimes. And I will probably make a video just about this. We're dealing with that guy right there. We're dealing with, I don't know what the audio did there. We're dealing with rectangular sections. It's not a problem to use a 1/4 inch thick steel stringer for stairs. The challenge is with how do you attach the guardrail. But other than that question of guardrail, it's fairly straightforward. Before I get to the calculator, I got to have my whoopsies, erratum, and notes. Basically, after I've uploaded this video, I can't really change it. So if there is something that I think could lead to something being unsafe, I'm going to take the video down. But if the video is still up, that means I thought that any errors I made were not that big of a deal. And so look in the video description, and I might have made notes saying, hey, I screwed up. Not that I would ever screw up. I would never screw up. On to the easy way. For your member, we've selected C12 by 20.7. Oftentimes we'll use this section because it provides more strength against the torsion when the guardrail is attached to your stringer and it wants to bend. The top flange of your stringer has to be strong enough to prevent any sort of plastic deformation at that location. And the C12 by 20.7 is often strong enough that you don't need to weld on additional stiffeners wherever you get a guardrail attaching. Typically, the code requires a 300-pound point load anywhere along the stair. We're assuming in this calculator that it's occurring at mid-span. Your elephant is going to cost, the elephant costs a lot of money, so don't buy an elephant unless you can afford. So don't buy an elephant unless you can afford its maintenance and upkeep. Elephant veterinarian's very expensive, much more expensive than my cat. So let's find out how much an elephant weighs. Weight of a full-grown elephant. Kilograms. 4,000 and 14,000 pounds. Now, we are going to assume, because it's an elephant, that it can't apply all those 14,000 pounds at one point. The most you're going to see is a 7,000 pound point load from your elephant. So we are going to up this from a 300 pound code point load for us Peasley humans up to a 7,000 pound point load. Now, at this point, our 120 pound per linear foot PLF of dead load along the stringer seems a little bit inconsequential. But if you want to go into the nitty-gritty details of how to calculate that, look for the link somewhere above me, and that's going to show you how to calculate that dead load. This is the area live load. Under the stairs, we're assuming 4-foot wide stairs, so 2 foot of the stairs is tributary to either stringer. And if you have 100 pounds per square foot, then that is 100 pound per 200 pound per linear foot live load along that stringer. And of course, this just sums up the dead load and the live load for the calculations below. And here we have a 17-foot long stringer. So you go through. I'm not going to step through each of these in turn. These are the calculations required, and they handle all the theory that we've discussed previously. But again, this is a very simplified case for beam bending for our stringers. If you've got stringers that aren't braced more frequently than whatever the unbraced length for your stringer member is, then this calculator is not going to work, so don't use it. Also, this calculator only used for steel. So, if you're trying to build some stringers out of wood, this is not going to help you. Not this calculator anyway. Should probably do a wood stringer video at some point, but that'll happen later. And at the end of the day, this stringer was strong enough. We are using 65% of the allowable strength. And in fact, we even meet code requirements for deflection. And now I'm curious, how long can this stringer be and still support our elephant? I don't think 300 inches is going to work. It did. Assuming braced 11 inches on center, you can have a 25-foot long C12 by 20.7 and have it work. If we use the slimmer MC section, by 10.6, then what would be the longest that we could do? Not the 25 feet. Can we do 200 inches? No good. NG. So if you see down here that it says NG, that means no good. Can we do 150 inches? Almost. It's kind of within the error, so 145. So you can go 12 feet. It says no good, but 1% over, you're fine. And so there's your answer. Now, it depends, obviously, on your stringer section, but if you got an MC12 by 10.6, you can have a 12-foot long stringer before your elephant is going to break it. If I was really checking this, I would want to know what the bracing force was. Probably the welds to the risers that we showed earlier are going to be adequate, but the more force that is in the section, the stronger your braces need to be. And in this case, the stronger those welds need to be. So if I was really honestly checking that an elephant could walk on these stairs, I would check the bracing strength. So don't put your elephant on any stairs based on this video. Hire an engineer, because this is not stamped and this is not engineering advice. This is for educational uses only. And with that, I thank you for your time watching this silly video, and have yourself a good day. One more thing. If you want to use this calculator, there's a link in the video description. So you can use this calculator.